Okay, now what are AVR microcontrollers? So you can see this usually as a kaning ATX Mega. Kita na mo ginani. Wala pa. Ano din sa microcontroller? Sa Arduino rather. Katong saba na siya. Ano to eh? Kabalo na ako ATX Mega. Yes, sa Arduino. Or di ko sure, Arduino ba ni? Yes, sa Arduino. ATX Mega siya. Kaning ginagamit. Naka-embed sa chip dito sa Arduino board. So this was developed in 1996 by Atmel Corporation. The structural design of AVR was developed by Alf Egil Bogen and Vegard Vollen. AVR derives its name from its developers and stands for Alf Egil Bogen Vegard Vollen RISC microcontroller. Wow. So it's also known as the Advanced Virtual RISC, wherein the initial microcontroller developed under this type was this one, kanang 8090 and so on, in the year 1997. So the general architecture looks like this. This architecture actually is a Harvard architecture. So yes, again, our Harvard architecture siya. This a type of computer architecture with separate memories and buses for program and data. No? Instructions in the program memory are executed with a two-stage single pipelining scheme. While one instruction is being executed, the next instruction is prefetched from the program memory. This concept enables instructions to be executed in every clock cycle. Kanina naman is how the instruction execution is the instruction execution timing. So this diagram shows how multiple instructions are processed in overlapping stages. No? The stages include, we have the fetch, read, process, and write. This is the, I made mention earlier, the execution or the cycle. No? So again, this is the instruction execution timing. So how does it work? Now, in this diagram here, you can see the clock indicates the clock cycles na T1, T2, T3, T4. Each clock synchronizes the instruction stages kani. Okay? So kani siya, kaning instruction fetch and execute. This shows how the CPU fetches and executes instructions in a very staggered manner. So first instruction, kaning first instruction here is fetched in T1 and executed in T2. The second instruction, it's fetched in T2 while the first is executed and it's also executed in T3. So this overlapping continues for the third and fourth instructions. Now here in the lower diagram here, it visualizes the pipeline stages over time. So T1 fetches the first instruction, and then T2 executes first instruction while gina-fetch niya ang second, no? That the T3, the first instruction completes the read, process, and write, no? While the second is executed and the third is fetched, T3. And in the T4, we can see that it's already the pipeline continues, no, with multiple instructions being processed simultaneously. So it is fetched on T4. Okay, so we have talked about pipelining here. What's ba ng pipelining? Pipelining is the process of overlapping instruction execution stages to improve the CPU throughput, no? So that there will be no overlapping, so instruction overlapping. Because an instruction overlapping is as one instruction is executed, another is being fetched. So execute, fetch, para ma-maximize ang CPU utilization. So why do we need to use pipelining? First is it increases instruction throughput without increasing the clock speed. Efficiently, it utilizes the CPU, which can minimize the idle time. So ginagamit yun siya no, in modern processors to enhance in performance. We also have the fast access register file. It contains a 32 by 8-bit general purpose working registers with a single clock cycle access time. So 6 of the 32 registers, kani siya kaning box din can be used as 3 16-bit indirect address register pointers for data space addressing, which enables efficient address calculations. These are called 16-bit X, Y, and Z registers. So, kani siya ang general purpose registers. The general purpose registers include the addresses, no? So most of the instructions operating on the register file have direct access to all registers. And most of them are single cycle instructions. The immediate values can loaded be only in kani 60 R16 to R31, so immediate values. Ang 26 naman to 31 can be used for pointers, for pointing. Each register is also mapped in a data memory's address space. So X, Y, and Z registers, kani siya have added functions to their general purpose usage. These registers are 16-bit address pointers for indirect addressing of the data. So the arithmetic logic unit of this gani, architecture, of this architecture no, of AVR microcontroller, again, see, AVR is a Harvard architecture. So ang ALU ni Harvard architecture or ni AVR specifically supports ALU between registers or between a constant and a register. Single register operations can also be executed in the ALU. After an arithmetic operation, the status register is updated to reflect information about the result of the operation. So this is how the single cycle ALU operation is being done, no? So the status register contains information about the result of the most recently executed arithmetic instruction. This information can be used for altering program flow in order to perform conditional operations. So we have 7 bits, 8 bits rather, from 0 to 7. Okay, so these are the read, write, and the initial values here. So ang bit 0 is the carry flag, then bit 1, 0 flag, which is very different, right? It's very different from the 8086 na itong na-learn. But if you quite understand that, then it's very easy for us as well to understand the other architectures. Flash program memory in the Harvard architecture. So this is divided into the boot flash section and application flash. The boot flash section sets an environment for the application flash section codes to execute. The usual program memory allocation ranges from this one, kani. SRAM data memory. Si SRAM data memory, kung sa'yo na SRAM, it's static, no? So there are 2,303 data memory allocations available in this microcontroller, the 80 mega 328P. We have 32 register files, 64 standard I/O registers, 160 extended I/O registers, and 2048 internal SRAM. So it's pretty much very huge as to when we compare it to other katong microprocessors pa lang, no? Because this is already a microcontroller. So meaning to say that there is already a lot of things happening in this, no? Dagan mga components, and it's already been upgraded because of the researchers. Nakita silang way to minimize the size of and the size and the speed rather of a computer. So in summary to our lecture this afternoon, we are almost done. Actually, we're done. Microprocessors are integrated circuits which has only one CPU inside them, while ang microcontrollers have the CPU, in addition with a fixed amount of RAM, ROM, and other peripherals all embedded in a single chip. So two major classifications of microcontrollers, ISA are the RISC and CISC. AVR microcontrollers are RISC, no? RISC architecture microcontroller in the market since 1996, which has SRAM, on-chip programmable flash memory. We also have I/O data space and the EEPROM. What's an EEPROM? EEPROM is kana siyang electrically erasable programmable read-only memory. So this is still non-volatile, no, that stores data even when there's no power. So in other words, it's a user modifiable ROM. Ma-erase siya, ma-reprogram, no, repeatedly. Okay, so I think more to siya, no? Actually, kaning EEPROM is also it's used in computers. Usually, nagyo na siya sa microcontrollers such as the smart cards, remote keyless systems, or as a separate chip device. Again, it stores small amounts of data, relatively small amount of data lang, by allowing individual bytes to be erased and reprogrammed. So it's, kasi ang ROM na to, wala naman po tayo ROM, no, na pili siya erasable, programmable, electrically erasable, programmable. So this is far different from that. So yeah, I think that's it for today. So this is another architecture that we have learned, though, in microcontroller. Before Harvard actually, I mean after Harvard architecture, we before the Harvard architecture, we have the von Neumann architecture. So they differ. Si von Neumann was in 1945. Mm. Okay, so I think that would be all for our lecture for today. Do you guys have any questions?